I want to take a few minutes to talk about these questions. So first, we want to find the cutoff frequency of our input signal. So notice that here, the question gave us the band limit in the unit of hertz. Recall that omega is equals to 2 pi f. So we can calculate our cutoff frequency omega c is equals to 2 pi times 100, which is 200 pi. And we know our sampling period t is 1 over 200. So our sampling frequency is 2 pi over t, which is 400 pi. And we can see our sampling satisfies the sampling theorem. That means our signal has no overlap. It was preserved perfectly. The tricky part of this question is to how to understand this discrete time signal here. So let's think about if we have a continuous time signal, xt, and we use the impulse train to do the sample. What we get is a train of impulse with the different magnitude at certain time. So the sample signal we get is actually a discrete time signal, but with a continuous time magnitude. We can represent this continuous time magnitude using delta function. So we have this form of represent the sampled signal in a discrete time way. This is how this discrete time signal comes from. So from these equations that were given in these questions, we can also find out that the sampled signal, so this x and t is actually our sampled signal xpt. So we can find our signal using this equation when t equals negative t equals 0, t equals t, or otherwise. So we can use a summation of impulse signal and the time shift of impulse signal to represent our sampled signal. This is our sampled signal. It's a dt signal with a ct magnitude. What we want to calculate is xt when t equals this thing over here. So we want to know what xt is. To know what xt is, we have to do the reconstruction process. Recall what we learned from the reconstruction process. So we have the signal. We pass through a low-pass filter and we get our original signal. Remember what we learned? If we use an impulse train with a sample period of t to sample our signal, our sampled signal's magnitude will be 1 over t. So to make it look like our original signal, which is magnitude of 1, we have to go through a low-pass filter that has a magnitude of t. And if our signal was satisfies the sampling theorem, that means we were able to restore it perfectly. We usually use the sampling frequency, half of the sampling frequency as our low-pass filter band limit. And in this case, for this question, this t here is 1 over 200, and this cutoff frequency is 200 pi. So our x of t is equals xp of t and ht's convolution. From the convolution property, we know this is the inverse Fourier transform of xp j omega and h j omega. I'm sorry. Here I should write Fourier transform. But the good things for this question here is our sampled signal is a bunch of delta function summation. So recall the sifting property. Our x of p, t, and ht's convolution here actually equals 2 times ht plus capital T and ht and 2 times ht minus capital T because of the sifting property. Since we know what our ht looks like in the frequency domain, we were able to find its equations, its expressions. So we find our h of t expression is 1 over 200. This is the t magnitude, sine 200 pi t over pi t. So if you plug in this form in the equation above, you will get an equation with the variable of t. And then you can plug in the value of 0.5 over 200 to get what you want.